Okay, welcome back, everyone. I'm surprised that, little clap. Surprised that most of you are still here. That's, yeah, again, I thought I'd lose some people. Okay, so in this second part of the talk, I'm going to switch now a little bit and start incorporating some of the machine learning models into a control problem related to algorithmic trading. And in the last part of the talk, we'll look at reinforcement learning formulation of these control problems, which is in effect a model-dependent approach to things. So one of the pictures that we saw earlier is this order flow picture, this U-shaped diagram where on the horizontal axis, the top left panel there, the horizontal axis is time of day, and the U-shape shows us that there's activity mostly in the morning, it dies down, and then it speeds up towards the end of the day. And if you look at a particular day, which is the bottom left panel, you see that there's quite a bit of fluctuation intraday, as you'd expect, but it still has that U-shaped pattern. What I'd like to look at next, this is a question about how does this U-shaped pattern evolve from one day to the next. And, oh, in fact, I think I didn't pull up one set of slides. And that we're going to do using what's called a functional principal component analysis. And there it is. Okay. Okay, so we're going to try to analyze, where did it go? Right, we're going to try to analyze, as I said, the dynamics of this from one day to the next. And we're going to do that using FPCA. Now, a lot of people know about PCA, principal component analysis, but probably not many of you know about functional principal component analysis. So, quick reminder, principal component analysis, how does it work? So if I have data that looks like this, scattered around in this two-dimensional feature space, then the principal component analysis tries to find which directions in data is the most variable and independent of one another. That's loosely what you can think of. So in the middle panel there, we can see that there's a direction that is kind of diagonal, going from the bottom left to the top right, and that's where most of the variability occurs, and there's an independent component that's going perpendicular to that. In the far right, you see that there's independence along the axis that's going from the bottom right to the top left, and then perpendicular to that. And how do you extract the PCAs is simply by looking at the covariance matrix and extracting the eigenvectors and the corresponding eigenvalues, ordering them according to the eigenvalues. The largest eigenvalue gives you the most variability, the next variability, etc. And each one of those components, and if you have discrete random variables, are viewed as, if you take the linear combination given by the eigenvector, that gives you random variables that are independent of one another. The quick little result is that shows this is, say, suppose sigma is this orthogonal matrix, and sigma is this positive definite matrix, then we can find an orthogonal matrix U and a diagonal matrix D, such as sigma equals UD transpose, and D has elements that are strictly positive. And this tells you that and the way to find it is simply by solving this eigenproblem. So the UKs, the columns of U will be the eigenvectors, and the eigenvalues will be the diagonal elements D. And if you create this linear combination of x's to form y's, this vector set of y's, and you do the little calculation for the covariance matrix, you end up with covariance of yi with yj is clearly dij. They're independent of one another because D is diagonal. Those are the principal components. So functional principal component is similar idea. What you want to do here instead is think of your observations not as just these discrete y1 and y2, but imagine we had y1 up to y10. Imagine that each one of these observations is a discrete observation of a continuous function with noise. That's what your data actually is. So underlying, imagine an interest rate term structure. You have some term structure, but you only have a few points on that term structure because those are the things that are traded. But if we imagine that there's an underlying function there and the data that you observe is a slightly noisy version of that, and then next day you get another function thrown at you that's pulled from a probability space, we want to ask the question, what are the functions in this function space on which the data tends to move that are orthogonal to one another, and which one is the highest variability? That'll be our first principal component, etc. So the way to do this is by saying, let's take our data. One way of doing this is taking your data and projecting it onto a set of basis functions. These are not orthogonal to one another. It's just saying, take phi here up to phi 1 to phi k, a finite set of bases. T is just an index for, in our case, we're going to think of it as time, because we'll think of it as from 9:30 to 4. Our observations are the dots. In fact, they're not exactly the dots. I'm not sure why it shows up like that, but in each one of these plots, there should be a circle and then a dotted line connecting to the next circle. So there are really discrete observations there, and the dotted line just connects you between them. We're going to take that data, and we're going to regress it onto some set of continuous functions, phi 1 to k. That'll give you a set of coefficients, alpha. Imagine you have this observation on day 1. Then on day 2, you have another set of data. You regress that. That gives you the second panel. Day 3, you get the third panel. So this is an example of 3 days in a row regressing this order flow this order flow data onto a set of bases. And I think we've chosen Legendre polynomials for this, because our data starts and ends 9:30 to 4, and we just rescale time to -1 to 1. Those are orthogonal polynomials, but it doesn't necessarily mean that our data are drawn from, or I should say that when we look at the variability of our data, it's a perturbation of these orthogonal polynomials. We'll see exactly what they become instead. So you just use least square and you obtain this regressions and this interpolation of the data effectively. Now, there it is. This is Legendre polynomials, just in case you don't recall what they are. They are those, the first 4 of them, including the 0. If you do this every single day, you get a sequence of coefficients. I believe we'd used 5 up to Legendre polynomial 4, so 4th degree. First component is basically a level, tells you how high order flow is on average. And then the other ones are all of the different wiggles and shapes that we have here, okay? Those coefficients evolve through time, as you see in the diagram. Now there's a question, are these actually independent of one another, or is there some autocorrelation in there? Well, just like when people look at interest rate term structures, what they often do is they just ignore that fact and just look at the data observed for the different maturities and look at those as individual independent observations and look at the principal component on that. It's possible to instead look at this as a time series, this regression coefficient, and then like an vector autoregressive model, for example, and then extract the dynamics of that. Now you incorporating the actual intertemporal functional data analysis. But we're going to leave that out for now, because there's already enough interesting things going on here. So we pretend that these are independent. The way that we look at functional principal component analysis is the analog of the covariance matrix for the discrete set of random variables is the covariance function. So you have this function k of s, which is a covariance of your data at time s to time t, and s and t are continuous here. And we want to make sure that there's some criteria that we need in order for some of the results to hold. So in particular, it's mean square continuous. This is the analog of our covariance matrix. And we would like to find the instead of eigenvectors and eigenvalues, you look for the eigenfunctions and eigenvalues. So k is some kernel associated with this covariance function. And that kernel operator looks like this. It takes any given function, f, and just integrates it against this covariance function. And we seek the eigenvalues and eigenfunctions associated with that operator. So there's an interesting result. So one thing that you can see is that, or not see, you have to show these things, but one result that comes out of this is that the covariance function admits a very nice representation where you can write k of st in terms of the product of eigenfunctions at 2 different points in time scaled by the eigenvalue. And these eigenfunctions are orthonormal. So they integrate to 0 unless they're the same, ij. Now, there's a result, this is called the Karun and Luth expansion, that tells us that if we find these eigenfunctions here and eigenvalues, we can rewrite the data, x, the continuous form of the data, in an expansion on those eigenfunctions. So these are functions, they're not random variables, while these coefficients are the random variables. And those coefficients, you can obtain them by projecting the continuous function using the eigenfunctions, just like a usual projection when you have an orthonormal set. And they have a very nice property. The xj's there, sorry, they have mean 0, and they are independent random variables. This is the analog to, here unfortunately the notation is slightly different. That's the analog to getting these y's which are independent and orthonormal. Okay. So what we'd like to do now is try to find, we want to estimate this size. We want to find an estimate for these size. And in order for us to estimate this size, we can't do an infinite sum here. We're going to truncate it. We're going to have a finite dimensional basis and dimensional reduced approximation for it. And in order to do that, we usually subtract out the mean of x from the data. And the empirical approximation of the covariance function is just as you'd expect. You take the empirical approximation that you have from your data. So remember, these xis's that show up here, those are the approximations that you obtain on every single day from the regression. So they're given by this kind of expansion here. Okay. Then, once you have that approximation, you can use something called Mercer's lemma that says that for this particular empirical approximation, there's also corresponding eigenvectors or eigenfunctions, which become eigenvectors here, and eigenvalues for that operator. Then, what we'd like to do is say, okay, our actual data is given from the basis given by phi, which is not the eigenfunctions associated with the kernel operator. What we would like to do is we'd like to find out what are the estimates of those eigenfunctions by projecting them onto the same bases that we've used for our data. So we want to find these coefficients for each eigenfunctions. If you just do a little bit of algebra, what you'll find is that this kernel function, or the kernel operator, sorry, can be, that should have been a script k there, reduces down to this simple matrix multiplication over the coefficients that you've estimated together with those weights of the eigenfunctions that you're after and this sort of weight matrix. Finally, this is some detail, but if all the details don't, if you don't follow all of the details, don't worry. The end result is nice and simple. Solving the functional principal component problem reduces to an eigenproblem, but it's an eigenproblem where instead of taking the covariance matrix, which would have been here, times u equals kappa j u, you get this funky little factor, which depends on this weight matrix from the previous slide, the estimated coefficients that you've gotten from your regression, and that is the effective covariance matrix. If the bases that you use are in fact orthonormal, the interesting thing is that this problem reduces to simply doing a principal component analysis on the coefficients of your expansion basis. So the idea, you have a set of bases that you project your data onto. We found how to write the eigenfunctions in terms of those same bases requires you to solve this problem. That problem, if those initial bases were themselves orthonormal, turns out to be project your data onto these basis functions. Now take those coefficients and do a principal component analysis on it, which is kind of nice. So how does this look for our order flow data? Well, it has a the first, second, and third principal components are interesting. Let's look at the top right. This shows the first principal component associated with order flow, this U-shaped pattern. If you look at the blue line, that is the U-shaped pattern that you see on average. The red and green are adding the first principal component plus 1 standard deviation and minus, or it might be plus 2 standard deviation, minus 2 standard deviation. I can't remember. And it does something that's a little bit surprising. You might think, okay, interest rate, if we think about what happens with interest rate term structures, there's sort of parallel shifts are principal component. Well, that's not quite the case for the order flow. Instead, order flow slows down or speeds up the slowest part of the day. That's what the first principal component does. So it either makes the U more like a V or more like a flattened U, which is an interesting result. The second principal component, this is for Intel, says that what it does is it pushes the slowest part of the day earlier or later. If you look at the bottom panel there, right, bottom left panel, it's moving the slowest part of the day to slightly earlier in the day or slightly later in the day. And the third one, either it pulls the slowest part of the day down, but if it does that, it pushes the beginning and end of the day up, or the opposite. So it either slows down, speeds up the slowest part of the day, but then slows down the beginning and the end of the day. So those are very interesting features that you wouldn't have guessed. Yes?
Sebastian, what are the corresponding singular values? I mean, how much weight do you have on
72%,
okay, it's upstairs.
15%, and 7.5%.
Okay, so with that, you're already at the level of about 90-something.
Yeah, that takes us to 90-something. Yeah. Yeah, so this explains most of the variability in there. Yeah. So I think it's a very interesting, interesting empirical result, and another fun little tool that you can use. Now, one can ask, well, why did I stop at 5? I used basis functions where I had five bases. Why did I stop there? Why not 10? Well, there's some interesting, again, machine learning type methods that you can use to try to optimize over what is the correct number of basis functions to use. And that's the subject of a whole other talk. Then you can also incorporate functional components as well as categorical data and combine that together in order for you to model whatever features you want. But I just wanted to show you all some interesting result for FPCA type analysis, because I think it's underused in finance, or at least in math finance, financial engineering. And let's get on to the next topic here. So that's the same thing I saw before. Okay, these are plots. Oh yeah, we have not seen these plots. So as I said, what I want to do now is I want to tie in some of the work that we've been doing into an algorithmic trading problem, pose it as a stochastic control problem, solve that case, and show you how some machine learning methods tie into it. Then also go back to a reinforcement learning formulation of it and show you how that works. So for the stochastic control approach, I need to specify a nice simple model for the dynamics, a tractable model for the dynamics. So this is one approach to do it. What I'm showing you here on the horizontal axis in the top left panel is the difference between buy and sell order flow for 5-minute periods every day, every 5-minute period of the year. On the vertical axis is the price change over that same 5-minute period, and that's a scatter plot. And what you clearly see is a positive correlation between order flow and price changes, as you would expect. Okay? But not only is it a positive correlation between the positive codependence, it is almost linear. If you flip the axis and condition on those 5-minute periods which have 0 price change and take the average of the order flow of those, it's almost identically 0. That's what this point here says. Take 0 price change, find the data that has 0 price change, and take the expectation. Now, if you take this point here, 5 cents, take those bins which have a 5-cent price change and select those bins, and again, compute the expected order flow that you see empirically, and it is whatever it is there. And that's how you generate this line. The confidence bands are due to the fact that there are many more points where the price change is closer to 0 than it is when the price change is closer to plus or minus 10. There are nonlinearities that show up towards the edges there, but within the low price change regimes, it's more or less linear. So we're going to use that model. The bottom panel is showing you the slope of that linear regression, or it's actually the inverse of the slope, for every day of the year. So it was estimated using the day, I think, between trading between 10:30 and 3, something like that. So chopped off the first hour or first and last half hour. And you can see it fluctuates around, but it's always of a particular order of magnitude. And the last diagram is just the, I think that's the residuals, to convince you that the residuals really are, the residuals or the regression above are reasonable. Okay, we already talked about this, so we don't need to talk about that. So now let's get on to the more math side of this talk. What we just saw, the order flow, says this. If we're going to write down a mathematical model for price changes, one model would be to say, okay, it's a martingale under the P measure, but we have to account for order flow. So let's add in our order flow because we see clearly order flow affects prices. So our order flow, if we're trading at a particular rate, nu is the rate that we will trade, the item in blue there, that's going to push prices up if it's positive, it'll push prices down if it's negative. Mu plus and mu minus is everyone else's trades. And we're going to be model agnostic as to what everyone else is doing. Okay. So they have order flow mu plus and mu minus, and you may have a model for that by looking at historical data. Maybe you see that if there's positive excess order flow in the next period, there will also be positive excess order flow, but not as much, perhaps. You can look at data and try to come up with a model for that. You can, again, use a machine learning model to underlie that. But we definitely have to incorporate this effect, this drift effect. Next, we saw earlier that there's this temporary type price impact from either naively from walking the order book or by saying if we send orders in a short time frame, it's going to have an impact. We're not going to receive the execution price, we're going to receive something worse than that, and the amount worse that we receive is given by that slope A. So A is the temporary price impact parameter. If someone trades at that rate, that's the price they will receive. Therefore, the total cash process from trading over some time horizon is given by the integral below. Nu U du is how much you've traded over some time interval, short time interval, and the coefficient in front. S plus A nu is the price that you pay for that. Nu being positive means buying, so it's a cost. So what we're going to do is the agent is looking to solve a problem of this type where they're trying to find the optimal strategy within some admissible set of strategies. So those admissible set are squareable strategies that are adapted to the filtration generated by the price process and their own inventory. And order flow as well is going to be incorporated in there. What are they maximizing? They want to maximize the expected value that they get from trading, so that's X capital T. They also may have shares by the end, so they want to account for those values. That's S capital T, Q capital T. But I want to penalize holding shares at the end. So I want this agent to end the day neutral, for example. They need to be flat. The third term there is this running inventory penalty, and it is a penalty that looks like it's the integral of the squared of your inventory. It looks like the terminal inventory has a couple of different interpretations. One is it's an urgency penalty, so if you want to get rid of shares quickly, the parameter phi is large. The other is that it's somehow measuring the variance of your cash process. It's not really variance, it's quadratic variation. And the third is that it actually stems from model uncertainty. So I'll just give you a little inkling of that idea of model uncertainty here. So the model uncertainty, it turns out, one way to account for it is to say, okay, let's look at this model. I've put down a martingale there, and I've put down a drift. Well, maybe the drift is not just this. There's something else there. Right? The martingale, let's swallow the martingale. Even then, maybe not. Maybe if there are jumps in the martingale, perhaps we got the intensity wrong. Maybe we got the jump size wrong. Whatever model you want to put down, there might be some model error there. So it's possible instead of having this performance criteria, get rid of that last term and solve a problem where we play as if the universe is going to throw a model at us. We're going to restrict ourselves to the case where the potential model the universe throws at us is within the same is equivalent to the model, the reference model that we've chosen, but it could be different. We're going to penalize that alternate model that the universe throws at us using relative entropy. So if it's really wacky, like if we estimate from data the intensity of price changes is once every second, but the universe is going to throw us a model where it's once every 100 seconds, that's far too low. That doesn't make sense. Or if it's happening 1,000 times a second, that's again far too high, doesn't make sense. We cannot have those models equally valid. So we will penalize models that are too far away from the reference model via this relative entropy term. The interesting thing is if you solve this problem, it gives you the exact same result as this problem. It's not at all obvious, but it does. Here's an example and here's what happens if you compute that IMPA part there. You find out what is the measure that you're protecting yourself from in sort of the optimal, once you found the optimal strategy and the optimal Q or candidate model that comes out of it. What does it look like? It looks like this. Has the same drift as what you thought, but you modify the drift by the parameter phi, which is what shows up in here. The inverse of it shows there. And it's minus phi times your current inventory. So the way to think of this is, if I have a long inventory currently, I trade as if the asset has a negative drift. And if I have a short inventory, I trade as if the asset has an excess positive drift. Because that's what will hurt me. If I have a long inventory, the asset's price dropping is going to hurt me. So to protect myself from my uncertainty in the model, this is the dynamics that the optimal measure picks out. This is an interesting result. So this is a result in a paper in SciAm by myself and two of my co-authors, Alvaro, who's at Oxford, and Ryan, who's currently at Washington. Next, let's see. I'm not going to tell you how we solve this problem. I'm just going to tell you the solution. So the solution turns out to be this. The optimal trading rate has the form where the first term is some negative deterministic function times your current inventory. This is called implementation shortfall, or it's protecting you from implementation shortfall. So it's protecting you from the difference between the initial price and the price that you eventually receive. That's the Omgren-Chris solution, if you're familiar with that line of work. The second term that shows up there, this is the order flow adjustment. This is accounting for the fact that you are not the only one trading. You are not optimizing other people's trades, but we are accounting for the fact that there is order flow there. And order flow is not just zero or a Brownian motion. It actually, it has some persistence, and if you have a model for it, you can determine how to compute this expectation. So as I said, the result is model agnostic. This result works for any model that you would like from you, even non-Markovian models. Okay, let's get some intuition for that term. You can see the coefficient in front is positive, and the expectation there is the expected future order flow given the information you have now, weighted by some weight factor, the ratio of the hyperbolic signs. So it's a weighted average of future expected order flow. And if that's positive, so the cinches are positive, so the only way it will be positive is if you expect in the future order flow to be positive. If it's positive, what do? You speed up your trading now. If it's negative, you slow down your trading now or increase your rate of selling. And that makes intuitive sense, because if you expect order flow to be positive in the future on average, then somehow you expect prices to be moving up on average, so therefore I should be buying the asset now to take advantage of that future push in price. And similarly if it's negative. It makes complete financial sense, but what this analysis, which I don't show you here, I hide it, but what the analysis shows is precisely how to do it. What is the correct analytic form to do? Yeah. So, yeah, so that ratio is the ratio of the permanent impact to this temporary impact. So actually that, yeah, there was a change of label in here. So K and A are the same thing. Yeah. There is one parameter here that is free. It's gamma. Gamma is effectively the square root of phi divided by A. So it's the ratio of your urgency or your model uncertainty to the temporary impact. And you can choose this. If you make it large, then you're going to be urgent, and then this, effectively, with gamma large, only the order flow in the next short little while is important to you. If gamma is small, then all of the future order flow is important to you. If gamma goes to 0, this ratio becomes the difference between how much time is remaining would be in the denominator, and then the numerator as well, wherever you're integrating from to the end. So that just becomes big T minus u over big T minus t in the limit when you have no model uncertainty. So in other words, you take into account all future order flow, all not equally likely, but in an almost equally likely way. Okay, so what I would like to, let me check, where's my time? 30 minutes. Okay, oh yeah, we have lots of time still. We have about 50 minutes. Is that right, George? Yes. Yeah? Okay. Okay. I'm not going to bother to show you the, I want it because I want to tie in the machine learning side of things. So that was a simple model, right? Fairly simple model because I haven't specified anything particular. So what happens now when there are latent factors? So this is the result. This next set of slides is from a paper that's coming out in Math Finance on partial information and algorithmic trading, where we take this order flow idea, which is another paper that I had with Alvaro Cartea. This one is with Philip Casgrain, one of my current PhD students who's about to finish. So we have said that let's take a look at a model where the factors driving prices are latent, or at least there are latent factors. How do you trade now? So perhaps so A there is this potentially a stochastic drift that depends on a latent factor theta. Theta is a hidden Markov model, for example. Okay. In fact, in this paper, it is a hidden Markov model. We've generalized that afterwards, and that talk will be tomorrow. Okay. So here you have a latent hidden Markov model, and the asset prices drift depends on that. So you might think, for example, theta could be 1, 2, or 3. When theta is 1, the drift is 0. When theta is 2, the drift is 1. When theta is 3, the drift is minus 1. So you're in a neutral regime, positive regime, or drift up or drift down. Alternatively, you can think of it as a mean reverting model. Perhaps in regime 1, the price has no drift and is kind of a Brownian motion. In regime 2, it mean reverts. And in regime 3, it mean reverts to a different level at a different rate. Okay? Those are all possible models that fall under this class. As well, there is a jump process. So if you don't like continuous parts to the process, so in other words, you don't like this dt term, you don't like this dw term, well, turn them off. You also have a pure jump component, because in reality, prices are living on a grid. Depends on the time scale that you're thinking about what is important to you. So this is why we looked at the general form. If you're looking at slightly longer time scales within a day, maybe Brownian motion type models are okay, and you don't want the jumps. But if you're looking on a shorter time scale, maybe you do only want the jumps. Those counting processes themselves are modulated by the Markov chain. So there's stochastic intensities that are running around, but those stochastic intensity for the counting process can switch depending on what this latent hidden Markov model is doing. Okay, we of course have some prior on what regime the world starts in right now. That'll be called pi. And the problem that the agent is solving is exactly the same. They still want to solve this optimal control problem. However, the set of admissible strategies is now restricted to the information which the agent can see. So the agent does not have access to the latent factor theta. It's hidden to them. They can only see price. Okay. So here you can think of the order flow that we discussed before as embedded into that stochastic drift A. But we don't know necessarily what regime we are in. So how do we solve this type of control problem? Well, there's a couple of things that you need to do. So remember, we're adapting ourselves to a filtration which is smaller than the filtration that is natural for the price process. Okay. So the way to do this is we need, first of all, to get an estimate of what regime are we currently in. And that means computing the expectation of the indicator that theta t is equal to some theta now, given the information that we have. So F is a small filtration, the one that we can see. G, which I don't know if I rewrite in terms of G here, but eventually we will, is a large filtration. So the key trick to compute this, there's a number of known ways to do it. There wasn't a specific form of this kind in the literature before, so we just did it ourselves. So you introduce some measures such that when you take the continuous part of the price process, that becomes a Q Brownian motion. It becomes a Brownian motion under that probability measure. Q is not a risk-neutral measure. It's just, I'm using that notation. And under that same measure, the counting processes, which we said have stochastic intensities and are modulated by the Markov chain, under this probability measure Q, we want them both, n plus and n minus, to have intensity 1. We can make it any intensity. You can make it a constant intensity, but 1 is just a convenient choice. So you need to construct such a probability measure, and you can do this, and then you're able to compute this pi. And let's not bother to go through the details. The result is that pi can be written as the ratio of this lambda processes, and lambdas satisfy a system of coupled SDEs, which are driven by the price process that you can observe. And these jumps you can also observe because you can observe when the price jumps, so you know them. You don't know what is driving the jumps. You don't know what intensity is there, but you can know when they are. And these are the, so the lambdas, J's, are the potential intensities that you can have. So if you solve the system of FSDEs, then you can plug this into pi, and you'll obtain this estimate. In some ways, this is similar to the filter that we saw in the hidden Markov model. But this is a continuous time object that is related to the latent Z process and computing the probability of Z given the X's up to that point in time. Okay, so there's a tie-in here between the machine learning side of things and here, and we'll tie it in even more afterwards. Okay, the next piece that you need to do is you need to, in some sense, project the stochastic processes that you have, which are adapted to this large filtration, onto the filtration that you have access to. So you need to show that, in fact, there exists some Brownian motion, W hat, and some counting process, M hat, which are F-adapted and have the properties that we want. So again, the details, let's not worry about it. What this does for you is, oh, actually I don't show the end result there. What this analysis does for you is it shows you that you can rewrite the price process. Let's go back to the price process here. You can rewrite this price process in terms of stochastic processes that you can see. There's a reformulation of them in terms of objects that you can see. Once you do that, you've changed a partial information control problem, which is the one that you're after, into a full information control problem. And after a bunch of analysis, which I'm hiding here again, here's the end result. Very interesting. It looks almost precisely the same as what we saw for order flow. So what's happening there? The first term, again, implementation shortfall, the Armgren-Chris solution. Excuse me. The second term is now it is the expected filtered filtered drift plus the difference of the stochastic intensities for the Q counting processes, weighted again by those same ratio of hyperbolic signs. Once again, this has the interpretation of the expected future, not order flow, but net drift of the asset. Because before, order flow was the only thing driving the drift. Now it's some arbitrary set of stochastic processes together with the difference of the intensities of the up movements and the down movements. And it has the same interpretation as before in terms of if this is positive, then you trade faster. If it's negative, then you slow down or sell faster, depending on the sign that, that nu already has. Okay, here's an example. Yeah, here's a particular example of a model. This is a model where there's no Brownian motion and no drift, but we wanted to construct an example which is a pure jump process that mean reverts. And it mean reverts to levels that we don't know. So n plus and n minus are our counting processes, and they will have intensities given there. So A is a constant, not the same as the temporary impact parameter, and kappa is some constant. Theta is this Markov chain, and the subscript plus means the positive parts of what's in the bracket. The subscript minus is the negative part of what's in the bracket. If you look at this and you say, if you rewrite ds in terms of the martingale component and its drift, what you will find is that the drift is exactly kappa times theta minus s, which is what you normally have for, say, an Ornstein-Uhlenbeck process or a Feller process, etc. It's something which pushes the price somehow towards the level theta. But the prices all live on the grid. They all live on a grid because it's n plus minus n minus. If s is currently above theta, there are more down jumps. And if s is below theta, there are more up jumps. But theta can move. So this is the simple example. We can estimate pi online, etc. Here is, this is a better picture. Good. Yeah. So this is an example of simulation. So we've simulated from this model where we estimated from data. And the top right panel is showing us the estimate of the filtered posterior probability that we're in the various regimes. What we did is we artificially made the simulation be in regime 1, be in model 2 first, and then switch to model 1 afterwards, halfway, because we wanted to see, because if we know what's happening, then we can see, is our filter picking that up? And we start with a prior that's 50-50 prior, so the agent doesn't know what's going on. The simulation knows. It starts off in regime 2, then switches to regime 1. And what happens is that the agent becomes fairly confident, around, 70%, that it is in regime, that model 2 is a correct model over the first period, but it takes some time to learn that, and then towards the end, it also takes some time to figure out that it switched. But the switching, the learning rate is reasonable. Now, of course, this all depends on the particular model, on the particular data that you've used, and so on. But,
When you say online, you mean enrolling in adaptive window?
yeah, so the parameters are hardwired at the start. The filter is updated as you go through time. You could, in principle, simultaneously, as you update your filter, also update the parameters. But this is rather slow. There are ways to do this. In a real trading system, probably you don't want to do that. You probably want to assume some set of parameters, trade over some short time window, minutes, hour, then use that extra new data in the background to be updating the parameters and then start using them. And the various panels are just showing you some heat maps and P&Ls for the model. Now, mind you, this is data that's been, or parameters that are estimated from data, but run on simulation. So it doesn't account for the fact that when I actually put this into trading, people are going to react in some way. It is accounting for the fact that my trades impact prices because it's built into the model, right? It's accounted for that. But it's not accounted for the fact that people will react differently. Yeah. Okay, let's talk a little bit about calibration because it ties into the whole machine learning thing. So if we take a look at, let's go back here, this model. This is a continuous time with continuous parts and jump parts to the model. However, when we looked at the machine learning aspect, in particular for the HMM side of things, we were in discrete time. The observations are discrete. How can we potentially use the calibration or an model estimation from the HMM approach and tie it in with this continuous model? Well, the idea is fairly simple. You discretize slightly, you integrate over a short interval of time, but then you find that you can recast the model in this light. Theta is a latent state that evolves through time. F is the price that you see. It's a little bit different than the HMM that we saw in the past and traditional HMMs, because traditional HMMs don't have a closed circuit. Here, we have an arrow that connects F's to the one F to the next F. In an HMM, normally there's no connection between the F's. Conditional in the latent state, you get an emitted probability. You have a probability which emits one of the visibles, or the visible layer. So having that extra connection introduces some extra work that you need to do, but it's possible you can do it. You do something very similar to before. You have a completed data log likelihood. Now you also have multiple days on which you have data. So it's not just completed data log likelihood for one sequence of observations, but multiple sequence of observations. And that's where the sum over D is. And if you stare at it, and if you remember from before the break, this has a similar structure to what you had. The beast that shows up here, before, that object was just a matrix because we had discrete observations. It was the emission probability. Now that's a function. It's a function of the previous F, the current time, the parameters, etc. And what exactly is that function? Well, that function is the distribution function over one step. And that satisfies some sort of, that satisfies the forward Fokker-Planck equation, which you could either solve analytically if you have some nice models that you know how to solve analytically, or solve it numerically. And then you have an approximation for this G, which you then plug in to, into the analysis. So there's an M step, as before, where, or sorry, the E step, did I already do the E step? Yeah, the E step has been done here, where now those indicators have all been changed to, again, the smoother and the two slice marginals, which are defined below. The M step is pretty straightforward, just like, straightforward for two of the three objects that we need. One object, we need pi. Second object, we need Pij, the transitions for the Markov chain. Third object, we need the density, G, which is controlled by some parameters. In our case, in this example model, those parameters are A, kappa, and theta. In fact, in the implementation, we make A depend on the hidden state, kappa depend on the hidden state, and the mean reverting level depend on the hidden state. So all of those are parts of the parameters, and you don't have an analytic form for this. But one thing you can do is you can certainly do the M step by maximizing and getting pi and P. Getting G maximized, the third term, that's the hard part. There's some analysis that you can do, but then at the end of the day, you have to use numerics. You have to just use an optimization scheme. And that's what we've done. So there's forward message passing and backward message passing just as before, except the objects are a little bit different than ones we had. Yes, okay, fine, recursion. Let's look at some example now. 48 minutes, good. So this is Intel over 1 hour for all of January in 2014, and you can see this is purely discrete every time, and we've normalized it in the sense of we subtracted the price at the start of the hour. Now, if you do this latent two-state latent model using the pure jump model that we wrote down before, okay, the one that has the intensity that forces the prices to mean revert, we don't know if it mean reverts. Maybe the estimate for kappa is 0. Could be just to be always 0. Well, what we find, these are per second. We used 1 second time frame to estimate the parameters. So these are mean reversion rates on the time scale of 1 second. So you have to multiply that, say, by 3,600 to get time scale of an hour. So they're significant. These are the two regimes. They're fairly persistent, but there's a big difference between regime 1 and 2. Regime 1, this mu here, that is the constant, that's the constant intensity part of the intensity. Kappa tells me the mean reverting rate part, and theta is the level. So you can see in regime 1, mean reverting rate, or mean reverted level is positive, but you don't have a lot of activity there, and the mean reversion rate is half of what it is in regime 2. In regime 2, you have more intensity of up and down jumps. Mean reversion rate is twice as high, and the level is negative. So very different regimes, and quite an interesting estimation. You can go to 3 states, 3 latent states. Here you see something, something similar. Let's look at from regime 1 is, actually let's look at regime 3. Regime 3 is the most volatile state because mu is largest there. The constant in front of lambda is largest. Then the level that you revert to is negative. Significantly negative, in fact. Less significantly negative. Something is a little amiss. Sorry. Okay. And the mean reversion rate here is also much higher than it is in regime 1, while regime 2 is basically a Brownian motion. Right. It's got a much lower rate of mean reversion. But if it is mean reverting at all, it's going to mean revert to some level 3.5. Next, you can generalize this. Why univariate asset? Multivariate. Same kind of model, you can generalize and then do the same estimation. So here's the joint behavior. If I look at the joint behavior of these two things, this is Intel and SMH. SMH is a microchip manufacturing ETF. So Intel is one of the stocks in there. These had better be co-integrated. But how do you write a co-integrated model which jumps on a grid? It's not clear, not obvious anyway. So what we've done is we said that, well, let's use our same old model like this, except n plus and n minus are now 2-dimensional. You have jump up and up for Intel and SMH, down for Intel and SMH. The intensities for these two processes are, again, have the same form, but you have an intensity now for Intel and for SMH, and the same latent factor drives them. So if there is co-movement between these assets, and if they're co-integrated in some way, then the parameter estimates from one regime are going to see that perhaps both of them have high volatility. Maybe the Kappa matrix, Kappa is a matrix now because you have a vector of intensities. The Kappa matrix might have some interesting non-diagonal elements that introduce a codependence, and let's see what the estimate does. Here it is. Okay, so we did this just for the 2-state case for illustrative purposes. And again, now we see that regime 1 is a little more persistent than regime 2 from the A matrix because of this 0.92, that's 0.8. In regime 1, the more persistent regime, notice that Intel is pretty much not mean reverting at all, nor is SMH. Their kappas are almost 0. The matrix, is almost 0 entirely. This is a Kappa matrix. While in regime 2, all of a sudden, there is the Kappa matrices now have non-zero diagonals, and there's a slight negative off diagonal. But relative to the diagonals, actually the off diagonals are significant. But what this is demonstrating is that in the second regime, these two assets now have some kind of co-integration. It's also a much more volatile regime if you see the column corresponding to mu. This is a much more volatile regime. Okay, mean field games. No, we're going to keep mean field games for tomorrow. For Monday. For Monday's talk. Yeah. Well, this is analysis of a mean field game formulation of the. Let me say 2 minutes about it. So, in all of the models that we've studied so far, and in most of the analysis in optimal trading, people investigate single agents' behavior. We already know that all agents should affect prices through the order flow. And if there are optimizing agents and that are really playing a game, then that means there's many potential agents out there solving a stochastic control problem, which is really a stochastic game now, because my trades affect prices and your trades affect prices. Prices affect my profits. So we're all in a big stochastic game with one another. How do you formulate this kind of optimization problem with latent factors when you have many agents and I don't know what your inventory is either? I can't see that. I can only see prices. So there's latent information in many ways. One is how price moves. The other is what your inventories are, etc. Can we solve this stochastic game? So there's a paper that we have out there posted, I guess, a little while ago, a few months, on mean field games for algorithmic trading. What I'm going to talk about Monday is the generalization of that, which is not only is it that there's multiple agents interacting and playing the stochastic game, but different populations of agents have different beliefs about what model the world evolves under. So they have differing beliefs. So how do you solve stochastic control problems in that context? And we're going to use some really cool convex analysis tools. We got a nice review or survey of a lot of that from Teemu. There'll be no data in that talk. It's all just more or less, but fun. It'll be at a high level, so you'll get the insight. So that's what the mean field games is about, but I don't want to go there. We'll talk about that on Monday. So for the last, I think it's maybe 30 minutes, or sorry, not 30 minutes, 20 minutes left. I'm going to go to reinforcement learning. Is this it? No? I wish it was easier to see the titles here. Okay, there. Okay. So that optimal execution control problem that we just posed had a particular structure on the dynamics of asset prices, although it was very general. Right? You can fit a lot. In fact, it might be hard to come up with a model that doesn't fit nicely into that, that's realistic. However, it's still a model assumption. And it requires you to estimate those models, and then from data, and maybe the models change, maybe the dynamics of the world moves away from the models, even though you protect yourself from it by incorporating this model uncertainty, even though you have candidate models on which you have the latent factor driving and switching between that you're accounting for. One way, so there are still models there in some way, although as I said, we are protecting ourselves from it in from many different angles. However, an alternate approach to this is to not assume anything about a model and try to optimize in a quote-unquote online fashion, learning from the data while you're optimizing, or at least learning from the data initially offline, then while you're trading. This is the ideas from reinforcement learning is what I'd like to do. So as it says there, reinforcement learning, it's an unsupervised machine learning approach, unlike what we looked at when we saw classification problems, where you have a point where your observation is a feature and a label. Those go together. Here, there's no label, and you want to, as we did in the stochastic control setting, we want to ensure that we account for the action that we have on the system, the reward that we get, and the reaction of the system to that. So in general, we're going to look at a performance criteria like this. The notation is different from what I had in the continuous time setting because this corresponds a little bit more to what the machine learning community is doing as opposed to the math finance community. Right? So I have my foot in both these days, so I switch between them. So the term under the expectation, gamma is a discount factor. You can set it to 1 if you like, or to something small, sorry, 0.999. R there represents the reward that you receive by taking an action A at time step K when the system is in state Sk, and then it moves to state Sk plus 1. That is how you read this. So this is a reward taking action A when the system starts at time step K in Sk and ends up at this state, Sk plus 1. So this if you condition and starting at a particular point, this is the analog of what we would, in math finance, use as a value function. So it's kind of a value function, infinite time horizon problem. So script S is going to be the state of the system at time, and S sub t would be the state at time t. A is the action you take, and script A is the set of admissible actions. And the system evolves in a discrete time setting, so the new state of the system can be thought of being drawn from some distribution, which is given by F there, and ST is a previous state of the system, and A is the action that you take. So it's fairly generic. You just say the system evolves from your current state to some new state, and that evolution depends on the action that you do. That's general setup. Looks kind of like this. Top part of the diagram is the real evolution of the system. Bottom part of the diagram, S, is the states that you observe and that you use for your optimization problem. You take an action. So given your state SK, you take an action. That action affects what the new state is going to be of the real world, which also depends on the previous state of the real world. That emits a reward. That reward may depend on your current action as well. You don't have access to this full state of the world. Instead, you observe part of the world, Y. But perhaps you don't use all of Y in your observed states. Okay. So that's the way to read this diagram. It's a directed graph where your actions affect the real world gives you a reward, the reward depends on what action you did, you only observe a part of the real world, but you're not using all of that to make your decisions because it might be too much. Right? It might be too difficult, too computationally difficult, maybe there's extraneous information you don't need for whatever reason. So that's the setup. Okay, so reinforcement learning works via switching between the notion of exploration and exploitation. It's kind of like if you've never been to Rio before and you land there and you want to go eat, well, you kind of choose randomly restaurants. You don't know what's good unless you have a friend here, right? Then that's exactly. Then once you've, suppose you didn't know anybody and then you came here and you just start trying restaurants, Google doesn't work here, let's say, and yeah, you try restaurants and then you eventually, at some point, you figure out which ones are good and you start going back to those. And you do less of the random exploration. So it's the idea of slowly switching over from exploring possibilities, exploring what are potentially good actions, into those that you already now know are good actions. So in order to do this, what one does is you write this value function using the Bellman Principle. So there's clearly a Bellman Principle that applies here. It's a discrete time setting with just an infinite time horizon problem with some discount factor. If you just go through the little bit of calculation, it's pretty straightforward. The value function is given by the expected value. First of all, okay, you're going to take a maximization over actions there in a second, but you have the discounted value function evaluated at the state where you will be one step from now, given that you took action A and you started at state S, plus the reward that you got by taking action A, starting at state S, and then moving into this random state. So S1, excuse me, S1 is the random object here. Little s and A aren't random. You're going to choose A, which is why the maximum over little a is there. But little s is where you currently are in state space. But where you get to from your action, you don't know. It's a random variable. So that's why there's an expectation there. So that's a Bellman principle. If you know the transition probability of the states given an action, then you can simply rewrite that expectation as, replace the expectation with a sum over the discrete, and we're thinking of discrete states here and discrete actions. You have a discrete transition probability matrix there, and how do you solve this thing? How do you solve the Bellman equation? Well, you iteratively do exactly what's in that second equation. You take an h, you compute the sum over s prime of what's in the square brackets, then you choose the a that maximizes that thing. That's my new h. plug it back in, iterate. And this converges. You can show that this procedure, this is called value function iteration, and it will converge. However, it requires you to know the transition probabilities. That's the problem. That's what we wanted to avoid. That's where Q learning comes in. So what is Q learning? Q learning is the following thing. It's the observation that if I define this function, which is now what's sometimes called the action, state action value function, as opposed to the original value function, it's given by the expectation of the reward, the one-step reward, given that you take an action A at state S, plus the discounted future value function. Okay. And then take an expectation. If you look at that right-hand side, and let me go back, I think, 2 slides. It's exactly the right-hand side of this Bellman equation without the max. Okay. Remove the max. The right-hand side of that Bellman equation is what you call this action, state action value function, or the Q function. Now, if you replace H, you realize that actually the value function is just the maximum of the Q over A. Then I can also write this as a recursion for Q, or I can write this as a Bellman-like equation for Q. That's the second line. Okay, are we okay? I know that if you've never seen this Q learning thing before, sometimes it's not difficult. It's pretty easy math, but difficult to sometimes tricky to wrap your mind around it. So once again, what you could in principle do is, if you knew the transition probabilities, you just iterate this. But we don't want to do that. So what's the Q learning algorithm? It's, as I said, exploration versus exploitation. So you're going to take a random action with some probability epsilon k. K is going to index through time as you repeat the experiment. Just randomize your action, take it. You're going to observe what happens. You're going to use that observation to somehow update this Q function. I'm not telling you how yet. Okay, you're going to update the Q function somehow with that. And then, or so you randomize and then you take a random action. And if the coin flip told you don't exploit, then your current estimate of the Q function is what you use to determine what is optimal. So you just maximize over A, your current estimate of Q. So that's what it says here. So this is explore versus exploit. Okay, so how do you take advantage of this, or how do you update the Q? Here's the algorithm, and then I'll explain why it works. We won't go through the proof. The proofs are on the slide, but here's the idea. So you take initial estimate of the Q function, just random. That's often what's done. You just say, I have a table, right? Q is a table because S is discrete and A is discrete. It's basically a matrix. Okay, I put some random numbers in there. Usually normal 0, 1 is often a choice. You initialize the state of the world, and then you select an action with, that's epsilon greedy, so that means flip a coin, comes up heads, random action. Comes up tails, look at the Q function, where you are in the state space, whatever row you are, pick the action that is maximum. Take that action, whether it was a random action or not. So take the epsilon greedy action. Observe where you get to. Observe the reward. So that's S prime and R. Okay, so S prime is where you get to, R is a reward you got. Now update Q according to the formula below. So the right-hand side uses the Q that you currently have. That then gets plugged into the left-hand side. So what is it? It's somehow 1 minus alpha. Alpha is going to be a number that's going to go to 0. Your current estimate of Q plus alpha times the reward you received, discounted, and if you look at that object there, that max over Q S prime A is effectively your current estimate of the value function. So what's in the square bracket if I go back? What's in the square bracket is kind of like what's on the right-hand side of this equation without the expectation. Okay? Whoops. Okay, so you update the Q matrix like this. Now you update the state, because now you've observed S prime, that's where I'm currently at. Go back to 5 and just repeat. Repeat, 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 repeat. And you might say, why is this, what does this have to do with solving this Bellman-like equation? Because that's what Q should satisfy. Well, the proof is a little long, but there are some convergence requirements that you need. The alphas have to sum to infinity, and their squares sum to something finite. And epsilon decays down to 0. So the observation, the way to see why this is something that kind of makes sense at least, is to say, suppose you want to estimate the mean of a random variable x. Let's call that mu. I have a whole bunch of data. Well, I can do it, I can estimate it just by using all the data. That would be 1 over n sum of xi, or 1 over k sum of xk, if I observe up to time k. But now I can rewrite that in an iterative way in terms of my previous estimate, meaning using 1 data point less. And if you just do a little bit of math, do a little bit of algebra, you end up with mu when I have k observations is given by mu when I have k minus 1 observations plus 1 over k xk minus mu k minus 1. Okay, if you look at that and stare at it for a second, go to here, go to here. That's exactly what this is. Where q is the expected, where the random variable x is what's inside of the square bracket there. So it's effectively the same as this simple recursion. And 1 over k is your alpha k. Now, there's actually a set of convergence proofs that you have to do here, but given time, I'm going to skip it. Okay? I'll get you, you'll have the slides so you can take a look. But basically, you need to show that that operation is indeed a contraction. Okay? And there's a nice little proof, but then you need to show as well that this particular iterative thing converges. And then that takes some time to do. Okay, there we go. Q learning. So now next thing I want to talk about is Dinah Cue Learning. So Q learning isn't great all on its own. It doesn't converge so quickly. It's prone to not potentially getting the optimal behavior, etc. So one way of improving Q learning is using what's called Dinah Cue Learning. So Dinah Cue Learning, the idea is that you're going to simultaneously use the data as it comes in to update your model, but to update your estimate of Q, but simultaneously you're going to keep track of a model of the world. But the model of the world is not how we normally think of models in financial math. It's really simply the set of maps from S to S prime in the corresponding R. So it's kind of like a memory buffer. And you're going to sample from this memory buffer before you take your next action. So it looks like this. You initialize state, do epsilon greedy, okay, do epsilon greedy action from your current estimate of Q, take the action, observe this new state and the new reward, update Q according to the same rule as before. Here's a Dinah Q thing. Update model. So now you add in an observation. So you just have it's like you have a memory buffer. You have a new line in that historical data series, which is the state that you were in, the action that you took, mapped to the state you got to and the reward you got. And you keep that as a list. And now, before you take your next action, you take actions on this toy model that's sitting there, which is the list of actions you've taken before and the states you got to. So you randomize over this section. So you randomly select a state from your previously visited states, from your replay buffer is what it's sometimes called. You randomly select an action that you took when you were at that point in space, because of course you may get back to the same point and take a different action. In which case you're at the same state, but you took different actions and you got different rewards. In fact, that's how you're going to be able to update your Q function faster. And then then you find out where you got to, And then you update again Q, the same Q, this is not a different Q, this is the same Q, but it's being updated at different points in that action, state action pair. That's dictated by this replay buffer that you're just constantly sampling from. And then figuring out how many times to do that versus going to the next step, this is all art, really. There's no theory here.
Same reinforcement learning with options.
With options.
Option is like dynamical group when you work. Like you kind of store in a table
Mm-hmm.
the information that you find useful
Yep.
as employees run. Right? I don't have a refresh memory.
Yeah.
I don't know if it actually is comparable, just approach to the Q learning, because that options is a wider reinforcement learning, so it should work also for model days or
Mm-hmm. I'm not sure, so let's talk offline. Yeah. Okay, so here's some examples, and then I want to get to deep Q learning. And I think, how much time? 15 minutes? 7? We started late, right? Yeah. Yeah. 20 minutes at most. Good God, no. Yeah. Okay, you know what? In fact, let me skip going through the example and go to the deep Q stuff, because it's interesting there and there's examples there. Okay? So I'll skip through these. So, one of the problems with Q learning and Dinah Cue Learning is that when your action space and state space are continuous, it fails. You don't have a table anymore. You're only going to visit, even if you discretize your state space, but you have many states that you could potentially get to, and many actions, which is what you would think you would have in the real world, right? For a number of scenarios. It's not like an Atari game where you only go up, down, left, and right, which is where a lot of some of this work has been done. Instead, when this thing is continuous, you run into problems, convergence problems, and just in terms of sparsity as well. So function approximations are sometimes used, and one really nice approach to using function approximations is to use deep neural nets, okay, and use deep learning techniques. So how are we going to do that? So the Q function is going to be modeled as a deep neural net, and then we're going to do variations of Q learning with that. So what is a neural net? Because not necessarily everyone knows. Really, it's simply this. It's a map from an input layer to an output layer. And that map is constructed through a bunch of composite functions. So this is a typical example. We have an input layer, x1 and x2. Those are my input variables. They could be, price change and order flow or whatever you want. And then there are hidden layers, so the way that you interpret this map, okay? So remember, the top diagram is really, it's just fleshing out what do we mean by this composite function. It's simply a function. F of x, or y equals f of x. That's it. But that function f has certain structure. And the structure is that the value of x1 and x2 feed forward into h11, h12, and h13 somehow. I'm going to tell you on the next slide. And then the value of these nodes, which are called hidden because they're not the observable ones, not the input nor the output, feed forward into h21 and h22. And the value of those nodes feed forward to give me the output. Okay. That's generically what it is. Now, deep neural nets have many more hidden nodes at a given layer and many more layers. As long as you use 2, I think, 2 or more, then it's called a deep neural net. Yeah, it's just a terminology. Why this particular structure? One reason for this particular structure, it's motivated from a bunch of neuroscience type things, but how did it become so popular in recent times is because of this notion of using backpropagation, which allows you to estimate the model, estimate the parameters that feed into this network. Okay? So the set of network connections are driven by parameters. How? Let's see. So the mapping is composed of an activation function, what's called an activation function. So soft plus is one example. This is just, log 1 plus e to the x. Okay. ReLU, call option at 0. Okay. Right, call option struct at 0. Well, but of course then you don't have negative prices, so it's not exactly. It's hockey stick at 0. Tanh, these are examples of activation functions. Then there's a propagation function, which is often of that form. So it takes in a set of hidden values and outputs a number. And W transpose H plus B. B is the offset, W is the weights. And an output function, often the identity. And parameter estimation is what you call learning. So what you do is in this connection here, you, for example, you take these guys, you apply an activation function to them, and then you before you take the weighted average of these according to this propagation function, and then you push it through this activation function, and that's what tells you what H11 is, for example. So X1 and X2 are going to get mapped through this propagation function, and then it's going to get composed through the activation function. And then you repeat. That's all it is. It's nothing complicated. It's just a big composite function. But because it's a composite function like that, when you try to do optimization, when you try to find the parameters in the model that minimize some loss, that's the goal, big goal of this, is that you use this back propagation because of the way that functions compose. So you can compute partial derivatives from the end that feed into the ones before, that feed into the ones before that, and that gives you the full partial derivative. Why am I talking about a partial derivative? Well, remember earlier on when we used this gradient descent method that requires you computing partial derivatives of the parameters in your model. The same thing happens here. You have a loss function that you're trying to minimize. So you can do, the most naive thing you can do is, use the updating scheme that you have for gradient descent. So that's the idea. And then the question is, well, what is the appropriate loss function given a set of parameters theta? Now, there's tons that we can talk about with respect to deep neural nets all on their own, but I really want to focus on its use in this context of Q learning. So the way that we do it is we say, OK, let's go back to the Q function. Recall that it satisfies a Bellman-like equation, the one up at the top there. Right, there's no max outside. Right, there's just the, oh, OK, sorry, I've switched notation. Action is now little x. Okay, actually, because this is part of a paper that we're preparing right now that should be out, we hope, within a few weeks on optimal execution formulation using deep Q learning. Okay. And the previous set of notes are just generic notes on reinforcement learning. So these are taken from the paper, more or less. Okay, so so that's a Bellman-like equation, and recall it can be solved iteratively in the form that I had before. So I put this notation superscript L to denote the estimate at iteration L. Okay. So when we iterate, we go from L to L plus 1 to get us our new estimate. It's exactly the same update online equation that we have, and I've written it slightly differently. I've put only a factor of alpha there and 1 here. So this used to be multiplied by 1 minus alpha. I've just put it in here instead.
Sebastian,
yes.
Am I confused? Didn't you have the max outside expectation? Or?
Not for Q. The whole idea, let's go back to the definition here too. So H satisfies this Bellman equation.
Okay.
Q, on the other hand, is given by the expectation without the maximum term. And then it so happens that the term that's within the expectation has the value function, but the value function is the max of Q. So there's only one max there.
Okay, fine.
Okay, here. Okay, so the idea of this deep Q learning is that you view the current estimate of Q as a function of state and action as a fully connected neural net. Okay, so very much like, what does fully connected mean? It just means that every hidden node is connected to the next hidden nodes, and every one of them. Because there's no reason why a priori it has to be that way. I could, for example, cut off this connection here and that connection there, right? Both of those I can just throw away, for example, and I still have a perfectly valid model. It is a neural net, but it's not a fully connected neural net. So fully connected just means all of the hidden nodes at layer 1 are connected to all of the hidden nodes at layer 2, etc. Okay, so we write it like this instead. So QSX, it looks like a conditioning thing, but it's not conditioning. It just means that's just where the parameters go, to the right of the theta. Again, it's typical notation in the ML community. So the loss function, now, what is it that we're trying to remember? We're done through minimizing some loss, right? The parameters are going to be estimated in that way. Well, what does it mean? What does the loss mean here? Well, the loss is effectively trying to minimize this deviation. If you look at the top equation, if I take Q to the right from the top equation, I get 0 equals expected value minus Q. Right? Top equation, take Q off to the right. I get 0 equals expected value, square brackets, minus Q. Now, remove the expectation. Just take a sample. I'm trying to make that as close to 0 as possible. It's, in essence, it's trying to find the value function Q which satisfies the Bellman equation as close as possible. Okay, so the loss function is that. Here's where my new network parameters are going to be. Here's where my previous network parameters are. So before we had a Q table. We update that Q table one element at a time whenever we get a new action and a new reward. And when we do Dinah Cue, we do a bunch of them in between taking a real action. Here, what you do is, well, that discrete thing is no longer discrete. It's parametrized by the network. So I have an estimate of the Q function via the network parameters. I now am going to update those network parameters via minimizing this loss. Make sense? At least at a high level? All right. So remember we said when we did Q learning, which that's what this would be, this is deep Q learning, I mentioned that, well, you can improve it by doing Dinah Cue, by keeping a replay buffer and then iterating over things. Well, you can do the same here. So what you do is you have a replay memory, and that's just, again, keep track of all of the action state pairs and the rewards and new actions and new states you got to. But in order for this to work and to be kind of stable, you need to do this little trick where you don't, okay, how do I describe this? So let's look at this loss for a second. So here's a sum over, I'm going to take samples from my replay buffer. This is like iterating in the Dinah Cue part. I'm squaring the deviation of my Q function to the reward plus my current estimate of the value function. Okay? That's exactly like here. How does this differ from this place? How it differs is that, notice that there's a highlighted theta t there. Here, it was theta L that shows up in this part. There, that's theta L. Over here, we have theta t. That's the key, that's the only difference. And what's the difference between theta t? Is that theta L is updated every single time, because I go from theta L to theta L plus 1, then theta L plus 2, da 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 da. So the network is constantly being updated what my target Q is versus what my current estimated Q is. It's constantly being updated. It introduces a bunch of noise, and it's unstable. Or I should say, in different examples, it tends to be unstable. So one solution is fix the network to a target network. Run the Q learning on a model Q, a model theta. So theta is going to be updated from one step to the next in the usual way that you do in Q learning, which is, in this case, a deep Q learning, sorry, which is minimizing this loss as you observe data. And then every now and again, switch and update theta t to the model theta. It stabilizes the algorithm. so that this function isn't constantly changing every single time a new data point comes in. Okay? The function, remember, as a function of its two arguments, what determines that function is the network parameters. So we freeze the network parameters for a while we update a model network. So we keep a model network in the background that's constantly updating there, but it's always targeting this theta. It's not that theta m is targeting theta t, it's that theta t is being used to tell me what's my current estimate of the value function. Then by the end of it, say you do 5, 10 iterations, now you change theta t to be the theta model that you've estimated so far. So this is a stability thing. So one final generalization. Whoop, what happened there? That was weird. One final generalization is that it's actually a good thing to decouple this notion of taking an action and deciding which one you want from what's the value of taking that action. This is double deep Q learning. Okay, so yeah, I know there's a lot of like terminology just being thrown at you that seems weird, but it's not difficult. What you want to do is you modify your Q estimate now. So this is your theta t from before. Here, what we had done here is we use the max of Q. That's what we were always doing. Instead, what we're going to do is we're going to choose this optimal action to be given by the optimal action dictated by your current model. Okay. In this stabilization, when we do the replay buffer, you're freezing the target network, but you're choosing in this maximum here, you're picking sort of an optimal action based on the target network, although you're updating theta m. Now, what you're doing is, you're still going to be updating theta m, you're still freezing the target, but the optimal action is being dictated by what the target is currently. That's the distinction. And the loss is as you expect. It's exactly the same like before, except, like I said, this is x star. Okay, this is double deep Q learning. And here's an algorithmic version of it for the particular optimal execution problem. There's lots of nuances that we had to develop in addition to what I'm telling you to get this thing to fit within the framework of an execution problem. What we used was, in terms of features, we just wanted to keep the feature space low dimensional so that we can understand and make sense of it. We used time, of course, inventory, time remaining inventory, current inventory, quadratic variation over the last period and of price changes, and price. Okay, those are the features that we have. And in this particular case, we've sliced up the optimal actions into quantiles. So we took 3 different quantiles of the quadratic variation of price and chopped it up into 9 blocks. And just so that you can see that as you move to higher quadratic variation, you tend to execute actually a bit faster here. And as you move to higher prices, you also tend to execute faster. That's the generic feature that we find. And this should be the last slide, yes? This is just a result, sample result for one asset, where we ran the double deep Q learning methodology and compared it. It's unclear what to actually compare it to, because a priori we're not putting any model on anything. So what model do you use? So we thought, okay, just for at least for now, let's compare relative to TWAP over the time frame that we want. We could also use VWAP or something, but for now, this is what we've done. And you can see that the delta P&L there means take the profit and the profits that you receive from selling a bunch of shares, subtract that from what you'd receive for TWAP, divided by that from TWAP times 10 to the 4. This is the basis point savings that you would have. And you can see if we use just time, inventory, and price, The median is 3.39, that's the mean, that's the standard deviation, and you win 60% of the time. If you include quadratic variation, that goes up quite a bit, and you beat 71% of the time. If you include, oh yeah, delta P, right. If you include the price change from the start of the day to the start of your trading, so in other words, it's a measure of kind of the trend so far for that day, then you increase a bit more, and you beat approximately 90% of the time. And that, up at the top are the histograms of that difference. Okay, so I think my time is definitely up. I hope that opened up some of your eyes who've never seen any of these things before. There's a lot of interesting applications and methods, and even not just applications, there's a lot of things that are unknown of how to even do in this context of taking machine learning problems and putting them into financial math problems. In fact, I'll give you an example of one of the things that we're doing. There's a question of, well, imagine I have games, stochastic games. How do you do a reinforcement learning version of a stochastic game? There is work somewhat on that, but very sparse. And what about taking things like variational autoencoders, which take your features and project them onto lower dimensional explanatory variables, and on this low dimensional space, write down one of our cool analytical mathematical models that we can actually do analysis on, and then project that back up to give us and replicate the features that we started with, so that you can use some of the analytical control methods tying in together with the with machine learning methods. And then there's a host of things. So with that,
Okay.
thanks for your attention.
Thank you very much, Sebastian.